Okay, rewriting expressions involving radicals and rational exponents. For the first page, they want you to write each expression in exponential form. It's currently in radical form. See how right now there's a radical? They want us to rewrite it in exponential form, which means we need it all as an exponent. Does anybody remember how to do that? Right, your exponent will be a fraction. So your base is still 2. But is it going to be 2 to the 5/3 or 2 to the 3/5? Does anybody have any idea how you could use your calculator to know for sure how the fraction should be ordered? But how could you use your, like say this question was on the ACT or SAT, how could you know for sure if it's 5/3 or 3/5? Type it in. Okay, watch. If I type in the cube root of 2 raised to the 5th power, this is what it'll look like. The cube root of 2 raised to the 5th power. And it equals 3.17. If I type in 2 raised to the 3/5, is that the same thing? No. If I type in 2 raised to the 5/3, is that the same thing? Yes. So that lets you know when you write it as an exponent, the 5 needs to be the numerator and the root number needs to be the denominator. So 2 to the 5/3. So for this one, currently it's in radical form. In rational form, what would it look like? Number 2. 10 to the 3/4. Okay, so for number 3, when I rewrite this with the exponent, what will it look like? 7 to the 2/3. And remember, for all of these, you can check them by typing in both versions and making sure you get the same decimal value. Okay, number 4. Right, this is an understood 1 out there, correct? So 10 to the 1/5. Okay, take a minute and finish 5 through 10 and then we'll move to page 2. Okay, let's continue. Page 2. Alright, number 11. How would you rewrite this radical as exponential? Correct. Because isn't this an understood 2 when there's nothing visible? That's why it's called a square root. So 7 raised to the 5/2. Okay, for number 12. We have 1 over, how do we rewrite the 5th root of 2? 2 to the 1/5. Okay, so you may see that as a correct answer. That equals that. Or they may decide that they don't want 2 to be in the denominator. They want it to be in the numerator. Does anybody remember how you can just move a number to the numerator? Right, you make the exponent negative. Yes, anytime you're trying to move a number to the top or vice versa, you just take its exponent and make it the opposite sign. Okay, so let's look at number 13. The first step would be to change the radical version of it to exponential. And what would that look like? Right, and now if we just want the 10 to be in the numerator, it has to be 10 to the negative 2/3. Okay, number 14, the first step would be to rewrite it as 1 over 10 to the 5/2, or 5/2, and then you could also rewrite that as 10 to the negative 5/2. Okay, take a minute and try 15 through 20, and then flip to page 19 together before we move on. Number 19, isn't this an understood 2 and that's an understood 1? So that would be 7 to the 1/2. Yeah. Guys, please stop talking while I'm trying to teach. Also, remember, you have a calculator. Couldn't you have just typed in the square root of 7? And then when you type in 7 raised to the 1/2, you get the same thing. Okay, next page. Now we're going the opposite way. They've given us the rational exponent form, and they want us to write it in radical form. So radical requires a radical. What goes up under it? X. What root is it? And it's all raised to the 8th power. Now, you're probably thinking, well, how do we check these? Because it's an x. If you want to check it, that's fine. But you can't type in an x. You have to just assign any number to x. So what number do you want x to be? Okay, so if I use x as 7, 7 raised to the 8/5 is 22.498. If I put 7 in this x, it would be the 5th root. Okay, let's talk about how to get a 5th root. Go to math, and then see that one that has just an x on the outside? Pull it up, but then in there you can type in a 5. And then we've said that our x is 7, and we're raising it to the 8th power, and we get the same thing. So even when it's an x, you can still check it. You just have to assign a number for x when you're checking it. Okay, number 2. We're trying to write it in radical form, so that means we need a radical. What goes up under the radical is root 2, but we don't really have to write the 2, do we? And it's all raised to the 1st power, but we don't have to write that either. So that's all you have to write. Okay, number 3. We're writing in a radical form, so what goes up under the radical? 10a. What root is it? Cubed, and it's all raised to the 1st power, which you don't have to write. Number 4. What goes up under the radical? 2b. It's what root? Which you don't have to write, and it's all raised to the 5th power. Okay, go ahead and finish out that page and then turn to... Well, 2n would be under the radical. The denominator is always your root, and then the top is always what it's raised to. Okay? All right, let's go to page 4. Any questions on page 4? Which one? 14? Okay, just keep working while I'm going over for people. All right, number 14. This one is a little bit different because only the x is cubed. See how the 3 is up under the radical with just the x? Does that make sense? So when you write it, all of that will still go back up under the radical. And then wasn't this all raised to the 1st power? So how would you rewrite that? Oh, hold on. I didn't mean to write that. I didn't mean up under the radical. I meant in parentheses. Sorry. And then, isn't all that raised to the 1st power? So you would do 1 over 4. Okay, any other questions? Can I re-explain that one? Well, see how the 3 is up under the root this time? It's not like outside of it. And it's only attached to the x. So when you're rewriting it, you just write 10x cubed. But then you raise it all to the 1 over 4 power. Are there any other questions off this page? Shh, I'm trying to teach. 18? 18? Okay, so first it'd be 1 over a to the what power? 1/2. Because look, isn't this the square root and then all of it's raised to the 1st power? And then you could also rewrite that as a to the negative 1/2. Okay, now turn to page 5 and let's start the new lesson. Okay, today we're going to start learning how to graph exponential functions. The equation for an exponential function is y equals a times b to the x power. Now, it makes complete sense why this would be called an exponential function, because your x is the exponent. That's why it's called exponential, because your x is the exponent. X is always time. Your a is your starting value. And your b is your base, which is also the growth or decay factor. You don't have to worry about that lab equation thing. We're not doing that. Okay, b is greater than 1 means that you're dealing with a growth. Okay, if your b value is greater than 1, it's a growth. which means the graph will go up from left to right. Okay, it'll still go left forever, but from left to right it'll be going up. If your B value is between 0 and 1, so greater than 0 but less than 1, it's a decay, which means it will go down from left to right. Okay, if you're, see up here in the equation, your B value will be a number. If that B value is greater than 1, your equation is a growth, which means it'll go up from left to right. If your B value is between 0 and 1, so like 1/2, 2/3, 0.75, 0.2, any of those will be a decay and the graph will go down. So what if I give you an equation like this? Y equals negative 2 to the x power. What's the B value? Two. Is it negative 2? No, because I just told you that the B value will never be negative. So what's negative? The A value. Okay, there's always an A out front, so this is technically negative 1 times 2 to the x power. Your A value is negative 1, which will cause a reflection. The B value is 2, though, which is a growth. Does that make sense? That's confusing to kids. A lot of times, they'll think this negative is attached to the 2, and they'll say decay. But the B value will never be negative. If you see a negative, it's on the A value. Okay? Alright, so now let's try some of these. Identify as growth or decay. Well, first, let's identify the A and the B value. For number 1's equation, what's the A value? 4. What's the B value? Which means this graph is a decay. Okay, now we're going to graph it. So in your calculator, you'll go to y equals, clear out anything that's in there, and then you just type in what you see. 4 parenthesis 0.2 parenthesis raised to the x power. Okay, once you have it typed in correctly, you'll hit graph. And see how from left to right it's going down? That's because it's a decay. Okay, now, let's get some points on this curve so that we can put it on our graph. How do we get some points? Second table will give you a bunch of points. Now, negative 3, 500. Are we going to fit that on there? No. What about negative 2, 100? No. Negative 120 you can't even fit, but since that's the only point left of the y-axis, I'm at least going to go left 1 and then just go up here and, just put a point just to show that it would be way up there. Okay, then after that, my next nice point, 0, 4. 1, 2, 3, 4. That point is also known as the starting point, or the y-intercept. Y equals 4 in parentheses 0.2 and then raised to the x power. Okay, now my next nice point is, well, it's not nice, but look, just look at the table for a second. If I go right 1, I go up 0.8. If I go right 2, I go up 0.16. If I go right 3, I go up 0.032. So as I go right on the x-axis, what's happening? You're getting further and further, closer to 0, so close that right here, when you make it over to 6 units, it's so close to 0 they write it in scientific notation. Okay, so you don't have to be precise because nobody's going to be able to get exactly 0.8 and exactly 0.16. Just draw your dots closer and closer until they pretty much just look like they're sitting on the x-axis. Now, will it cross through the x-axis? Watch. If I keep going right, okay, 3, 4, 5, 6, 7, if I keep traveling to the right, do you ever see it go below into the negatives? No. It's scientific notation because it's so close. There's so many zeros because it's so close to 0. But no matter how far I go to the right, it never goes below the x-axis. It just gets closer and closer, so close to 0 that they write it like that. That'd be like 17 zeros, right? Okay, so your graph is going to look like this if you connect these points. that what it looked like when we had a picture of it? Now, does anybody remember what it's called whenever your graph approaches something but then it just flattens out and rides right along it? Anybody remember what that is called? Remember, it's like an invisible boundary that the graph approaches, but then it just goes right along it forever. Nobody remembers that word? Well, somebody just said it. No, it starts with an A. Asymptote. Okay, it's an asymptote. Now, the reason the asymptote happens to be at 0 this time is because, look, in a few minutes we're going to learn how the graph can shift. Like if I were to add 2 on the end of this, every point on here would have shifted up 2 units, making the asymptote 2. But since there's nothing there, isn't it like plus 0, which is why the asymptote's at 0? Okay, let's look at number 2. For number 2, what's your A value? 2. What's your B value? So is this a growth or decay? It's also decay, because B is 1/2, which is between 0 and 1. So now let's graph it on the calculator so that we can put it on this same graph. So y equals 2, and then times 1/2, which I'll just type in as 0.5 to make it quicker, raised to the x power. So now I graph it. Okay, go to second table to find some points. And then I need to go back the other way because all of these are obviously very close to 0. So I need to go the other way. Okay, as you go to the right, I can see they're getting closer and closer to 0. But then look, I have a nice point at 1, 1, 0, 2. That point at 0, 2 is also known as my starting point or my y-intercept of this graph. Then I have a nice point at negative 1, 4. And I have a nice point at negative 2, 8. Okay, and then on the right side, you can just see that as you go to the right, 2, 3, 4, 5, 6, 7, 8, everything's just getting closer and closer to the x-axis, to 0. So you don't have to be real precise, just draw a bunch of dots that are really close to the x-axis. It looks like they're sitting on it. Okay, so this graph will look like this. Okay, why is the asymptote of this one also at 0? Right, because down here, is there anything added to the end? No, it's plus 0, which means the graph doesn't get shifted up or down. So its asymptote is at 0. Okay, this is what we consider the parent function for exponentials. Okay, you all know how graphs start with a parent function that hasn't shifted left, right, up, or down. With a parent function of an exponential, the asymptote will always be at 0. But then when you start shifting it, it'll move the asymptote. Okay, so now let's try number 3. What is the A value? And what is the B value? So this one's a growth because your B value is greater than 1. Now, that 4.2 represents a growth of like quadrupling. It's growing 4 times as fast. So let's graph it and see what that would look like. Y equals 4 parenthesis 4.2 parenthesis to the x power. Okay, it's a growth, which is why this time the asymptote's on the left side and it goes up on the right, because it's a growth. But see how the asymptote's still at 0? Because there was no vertical shift. There's nothing added to the end. It's like plus 0. So now to put that on the graph, we'll find some points. You can see that as you go left, that's where all the numbers are getting smaller, getting closer to 0, because the asymptote was on the left side. But as you go right, your first point is 0, 4, then 1, 16.8. So even though you can't really, none of these are really easy to graph, like we'll just put the 16.8 one up here. And then over here, don't they just get closer and closer to 0 each time? Okay, so it would look like this. An asymptote at 0, but then going up from left to right. Ooh. Okay, so now let's look at number 4. What's your A value? 4. What's your B value? 2. Is it a growth or decay? A growth. Okay, where do you think the y-intercept for this one's going to be? 4. Look, guys, every time, look, 4. So it crossed the x-axis at 4. I mean, the y-axis at 4. 2's in the front, so it crossed at 2. 4's in the front, so it crossed at 4. And then 4's in the front, so this one will cross at 4. However, this one's a growth, but is it going to grow as fast? No, this one's basically quadrupling. This one will only be doubling, which means it won't be quite as steep when we graph it. Okay, so let's put it on the graph. Y equals 4 times 2 to the x power. Okay, and then I'm going to really quickly put the last one on there so we can compare them on the graph. 4 times 4.2 to the x power. See how the red one got a lot steeper faster? Because it's quadrupling. Its growth factor is quadrupling. The blue one is growing, but only by growth factor of 2, so it's only doubling, which is why it's not as steep. Does that make sense to everybody? Okay, so let's find some nice points for that one. We're looking at the blue numbers this time. Okay, so on the left side, you can see that it's getting closer to 0. As you go left, it goes to 0.5, then lower to 0.25, then lower to 0.125, then even lower. So the left side is where your asymptote is. On the right side, you have a point at -2, or -2, 1's a nice point, then -1, 2, -2, 1, then -1, 2, and then your y-intercept will be at 4, and then over here is where it approaches the asymptote, so you don't have to be real precise about those points. It'd be impossible to anyway if you tried. And then you have a nice point at 1/8. So see how, even though like it's harder for me to draw it, it looks better on the calculator, I can see that this one's not growing quite as fast as the green one was, because this one's only doubling, this one's quadrupling. Okay, now turn to the next page. Okay, now we're going to start talking about transformations. Remember, the parent function is y equals a times b to the x. If I add a number on the end, what do you think it's going to do to the graph? Well, in this case, if I do plus k, what's it going to do? Up k units, right? Minus k will move the graph how? Down k units. Grant, turn around. Okay, now look right here. This plus k is little with the exponent. How do you think that's going to move the graph? Left k units. And so what do you think the minus k little with the exponent is going to do? Right k units. Okay, so we're going to graph it and tell the domain, range, and the behavior of the graph. For this one, what's the A value? What's the B value? So is it a growth or decay? A growth. Where's the y-intercept? That's the growth. 1 is where it's going to cross the y-axis. Okay, so now let's graph it to get some other points. Y equals 2 to the x power. Okay, see how it crossed through at 1? Because A is your starting value. And then it's a growth because your B value was 2, which is greater than 1. Now to find some other points, you just go to your table. You can see that on the left side of the x-axis, all the negatives is where it's approaching the asymptote. No, just second table. On the right side, we have some nice points. 1, 2, 2, 4, 3, 8. What did I say? 3, 4? 2, 4, I mean. And then 3, 8. right there. And then on the left side, I'm not going to be real precise because it's impossible to anyway with such a small graph to get them exactly where they should be. They just get closer and closer. Okay, so that's what your curve looks like. Why is it going up from left to right? It's a growth. Why is the asymptote at 0? The K value was 0. It didn't shift up or down, which means the asymptote stayed at the x-axis. Okay, what's the domain? How far left will that go? Infinity. So negative infinity. How far right will it go? Infinity. What about the range? How far down will it go? The asymptote will not let it go down forever. It'll only let it go to 0, but will it ever actually touch 0? No, it just gets closer and closer, so you put a parenthesis. And then it'll go up forever. Now for behavior, they're talking about in behavior. So they'll give you this part. You just have to know what it means. You'll fill in for the y's. What does x approach positive infinity mean? X-axis only runs two directions, left and right. So this would be right. As you go right, on the y's you're going up, so positive infinity. If I go to the left side of this curve, the y values are all approaching 0, the asymptote. Okay, we'll continue with this lesson tomorrow. You can switch out.